So we will move on to question number 10. So this is another place where we see the isomeric structures of inorganic compounds have been asked. So normally we discuss about the isomers in the organic question, but normally we don't teach them in the inorganic chemistry part. But it is very essential to understand the concept of even inorganic compounds can show isomers. Okay, so it can show isomerism. Even the optical behavior can be shown by isomers of inorganic compounds. Okay, so this question is based on such example. Okay, so we have 4 different coordination compounds. So I will use the board here because it will be easy for me to explain the question as well as the answers. So they have given, we have 4 different compounds, A, B, C, D. They are coordination compound, which means there should be a metal and they should be coordinated like this. Okay. They have an octahedral geometry. Okay, so this is the one. They should have like 6 ligands, octahedral geometry, and all the compound consist of a single chromium ion. So which means our metal here should be chromium, and it is in the ionic form. We don't know, it could be either +2 or +3. Okay, 3 chlorine atoms. So this contains 3 chlorine atoms. So we don't know where this 3 chlorine is going to present, either here or B, maybe outside the coordination sphere. We don't know. And we have could be either covalent or ionic. So basically they tell that story. It could be either chlorine, which is covalent, or maybe as Cl minus outside the main coordination sphere. Okay, for an example, if you remember about this compound ion, let's say CN6 3 minus. So instead of 3 minus, we can put Cl3, which means this is the sphere which has a 3 negative charge. And if this is +1, if this is -6, there is a -3. So this has a -3 charge. So if you want to balance this one, you can add 3 potassiums. This is one of the example that we normally know. Otherwise, if we have FeH2 or 6, 3 plus. If this is in 3 plus, so to balance this +3 charge, we can add 3 Cl minus. Okay. So for cation, there is a counter ion called the anion. And if the coordination is negative, which is an anion, there can be a cation, which is a counter ion. Okay. So here in this question, they say this chlorine can be, okay. Here in this question, they tell chlorine can be either covalently bounded or chlorine can be present as counter ion. That is the ionic form. We don't know what is. This shows the example of this counter ion being a positive ion and a negative ion. And also they say the molecules contain, the compound contain water also, and the number of water molecules also can be varied. Okay. And furthermore, chromium ion in all the compound, wait, I will share. So the chromium ion in all the compound has the same oxidation state. So this oxidation state of chromium in each compound is same. We don't know what is the compound. Okay. The number of water molecules changes. The complex ion part, metal ion to the ligand coordinated into it. It's okay. The charges of A, B, C, D are given. Okay, so that is one of the other additional things that they have given. This is +3, +2, +1, and 0. So the charges have been given. So the question says, give the oxidation state of chromium in the coordination compound. So you need to find the oxidation state of chromium. The advantage is we know normally chromium is present in either +2 or +3. This is the common oxidation state of chromium. We have higher also, but in coordination compounds, in general, we know +2 and +3. So either it can be +2 or +3. We don't know. Okay. So we need to find this. And next, they say write the electronic configuration of chromium in this compound. So this will become straightforward because if you find either it is +2 or +3 or even any other +6, maybe, I don't know, you can write down the electronic configuration. This becomes straightforward. Write the structural formula of ABCD. So we are going to find this one. That will be one first task. And give the IUPAC name of A. So this will be easy when we find the structural formula. Give a chemical test that could be used to distinguish between A and D. So we have to stop here because we have to find first A, B, C, and D. Right? So how you are going to find? This is very important to think. Okay. So we have the ligands Cl minus and water. We should have this one anyway. So when you have a chromium, and we have given all those are octahedral complexes. So we need to balance these ions and put into its coordination sphere. Okay, so this will be this one. I will draw like this. And this should have some charge. And as well as when you have this chlorine as its anionic form, let's say this one will have they have given the charges. So basically this could be like positive n for an example. We don't know. So there should be n number of Cl minus. So there when there is n number of positive ions, it's like +1 into n. Then here -1 into n. So the overall charge becomes 0. Okay. So this could be for this one. Because to get the overall charge 0, the compound should have this type of arrangement. For an example, FeH2O6 3 plus. So if we have Cl minus, it should be 3Cl minus, which should give you FeH2O6 Cl3. Okay. So this is one of the idea. To judge it's 0. So how you can get this as +1 then? It is additionally n +1, additionally n +2, additionally n +3, which makes the charge of this complex increasing. Okay. So the task here is using this Cl minus and H2O. We need to find what is this octahedral complex, because here there should be 6 ligands inside, because all those are octahedral. But these ligands can be H2O or maybe 5 H2O and 1 Cl within, and even 4 H2O and 2 Cl, or maybe H2O thrice and Cl thrice. So we don't know. There can be many combinations, even 6 Cl. The advantage for us is they have given the charge. So that is the main advantage. Okay. So we can use our combination of this chlorine and water to check the charges of ABCD. So A, B, C, D, +3, +2, +1, 0. But don't forget, oxidation state is still same. Okay, so we will check how we can get a zero charge using Cl minus and H2O, a compound with zero charge. Okay, so we can have chromium, so it will be the element. So we need to have 6 ligands in the structure. So if I put 3 water and 3 chlorine here, if this is plus 2, remember chromium plus 2 or plus 3, this is minus 3, and the overall charge will be minus 1. Here there will be minus 1. Okay, but there are no compounds that showing the overall charge minus 1 because we have additionally Cl minus, so we cannot put this Cl minus here because this is also minus, this is also minus, so that is a problem. Okay, so we can directly first of all conclude this cannot be the combination. Okay, so the compound that drew was H2O thrice and Cl thrice. So we saw here if this is plus 2, there is a problem. What if this has plus 3? Chromium can be plus 2 or plus 3. So if this is plus 3, there is minus 3, and the overall charge now becomes 0. Okay, think about this. In the coordination sphere, it becomes 0 now. This is one of the factors that you can determine. Okay, but this is of the coordination sphere, but we have to consider about the counter ion because this cannot be a aqueous solution. This could be a precipitate. Why? There is no charge for the coordination sphere. This is like how can I say, this is like a normal sulfur precipitate. It will precipitate out because of no charge. Okay, the idea that it forms a coordination sphere with a charge means the coordination sphere should have these charges. Okay, without the counter ion. Okay, so if we think about the simplest compound that has only water, so it will be chromium H2O6 with either 2 plus or 3 plus. So to balance this 2 plus, there can be 2 Cl, or to balance this chlorine, to balance this 3 plus, you can have 3 chlorines. So this is one of the ideas that you can take. Okay, so now all these things are additional. We have not discussed yet the question. Okay, here comes the story. So the maximum amount of water can be present inside is 6, which gives the octahedral nature. Then the charge could be either plus 2 or plus 3 because we don't know the oxidation state of chromium yet. So there could be 2 chlorine or 3 chlorine. So this is one of the compounds that can be present. What is the other one? That is necessarily need to be understood. The main point that you could miss in this question is the number of water molecules in the compounds vary, and this contains 3 chlorine atoms. So this is the important thing. Otherwise, there can be many combinations that I have already shown you. We can draw many combinations. So don't miss this point. This is very important to understand. In their compound, there are 3 chlorine atoms. Okay, don't forget to miss this point. Don't miss this point. It is very important to understand, because if you directly come to that conclusion where this compound should have 3 chlorines, automatically this is gone. Why? Then it shows only plus 3 can be accepted, and there should be 3 chlorines outside to counter this charge of plus 3, and hence chromium in our complex is in +3 oxidation state. Okay. Then think about the way how you can vary the number of water molecules inside giving a octahedral geometry. So that is important to give an octahedral geometry. Okay. For an example, I can send one chlorine inside. So if I send one chlorine inside and remove one water molecule, so this will be 5H2O molecules, one Cl here, and there should be 2 Cl outside. Okay, so this will be +3 and -1, and here overall charge is +2. So this is our structure, +2. Then if you change another one, chromium, H2O4, 2 Cl, and 1 Cl. So this is +3, -2, +1. So this will be our +1 structure. And finally, you can put chromium, H2O thrice, Cl thrice, +3, -3, overall charge is 0, which is our D, compound D. Okay, so think about the entire discussion. If they have not given the chlorine stoichiometry, we will be lost because we had many combinations that we try to reach. If you want to get the real structure, you need to know how much chlorine is present. Otherwise, the problem is you cannot determine whether chromium is +2, +3, or even +6. We don't know. So the advantage of giving the oxidation is same. That is first point. Second is octahedral geometry, and the third is 3 chlorine atoms. 3 chlorine atoms concludes our discussion and limits our discussion to this place. Okay, so that is important to understand. And now we have drawn, we can find the oxidation state, that is +3, we now already know now. So you can write down the stoichiometric, in fact, the structural formulas of ABCD, and then you can write down the electronic configuration, which is asked in the question. Normally chromium is 24, so 4s2 3d 4 is rearranged into 4s1 3d5, but here it is +3, so 4s0 3d3. So you can write down that one along with the entire electronic configuration from 1s to 2s to like that. And more importantly, what else they have asked? We'll check that very quickly. So give a chemical test that could be used to distinguish between A and D. Yeah, so we have to check that one also. So A is this, D is this. Is this D? Yeah, there should be 3 chlorine. This is D. So what is the difference between these compounds? So as I explained to you just before, a few minutes ago, I told you these are counter ions. So these chlorine atoms are present outside the main coordination sphere. So these are ionic, but here there are no ionic chlorines because the overall charge is 0, and this could precipitate out because no charge for this complex, right? So how to distinguish this? Because since this has ionic chlorine, you can add silver nitrate solution to precipitate this ionic chlorine as AgCl. But however, if you add AgNO3 for this one, silver nitrate, no precipitation will be happening because there are no ionic chlorine that is present here in D. Okay, so that is the way that you can distinguish between A and D. Right, so that is the way that you can distinguish. So IUPAC name of A, so A is this, so hexa aqua chromium 3, there should be a small space and then chloride. Okay, so you know we don't put this as trichloride because chloride, bromide, iodide all are basically with stable oxidation state, that is -1 here in this case. So we don't put this oxidation in Roman. We put the oxidation states for the elements where they have variable oxidation. For an example, chromium, we have +2, +3. So in that case, we have to write down the oxidation state in a bracket using the Roman letters. So we have given another important part here. So given below is the structure of the oxalate ion. So the oxalate ion coordinates in the chromium ion through two negatively charged oxygen. So they are going to coordinate like this, okay, to give a complex ion part E, which also has the octahedral geometry. Think about this. We have oxalate and it has two coordination sites. So octahedral should have 6 coordination sites. So how many oxalate molecules are needed? If one oxalate has 2 coordination sites and the geometry is octahedral, which means there should be 6 coordination that is happening to the metal ion, chromium. So each oxalate has 2 coordination sites. So 2 into 3 makes 6 coordination sites. Write the structural formula of E. So I will use the board. So basically what is actually happening here. So I will compare this compound A with the oxalate one. So we have chromium H2O6 3 plus. So we have chromium like this, and inside the plane and outside the plane and on top there will be 6 water molecules like this. Okay, so lone pairs are given like this. So this is the octahedral geometry. So what is actually happening here? So this is the plane. This is the plane. So we have this plane, and on top there is one ligand, and on bottom there is another ligand. So that is the octahedral geometry. Okay. Now here they have given the oxalate anion like this. So which is going to be coordinated to the chromium. So there will be chromium 3 plus still here. And if you think these two are these two coordination sites, there will be one like this, and there will be another like this. Okay, so all these going to coordinate like this. So this is how this 6 coordination is going to form. Okay, so there will be like a little bit of inconsistency in the geometry in the octahedral. So if we think that this is our plane, this will be one, and this will be in the bottom. Okay. Anyway, this will be like arranged in an octahedral geometry. So why we have to take 3 ligands? Because each oxalate will give 2 coordination sites. Okay, 2 coordination sites from this -1 and -1 oxygen. So here we have 2, here we have 2, here we have 2. So altogether we have 6 coordination sites, which is very similar to here. This is also octahedral. This is also octahedral. Okay, so in fact, if you check this compound, you would see this compound will show optical isomerism. They will change the rotation of the polarized light. Okay, so this is not actually at your level. We study this in university, but they have given a simple question based on that. Okay, so they are telling write down the structural formula. So you don't need to draw all these things. You just need to write chromium ox 3. Then what is the charge? So here chromium is +3. So this one would give negatively charged 1 and 2. Okay, so -2, -2, -2. So -6. So +3 -6, there will be -3. Okay, so this is +3. This is -2 times 3, -6. So -6 + 3 -3. This is the charge. Okay, But don't forget, if you put here ox instead of C2O4 chromium, you are going to lose marks. Why? Because in the question, they have given you, instead of C2O4 minus, use ox. So you have to mention using ox. If you use C2O4 instead of ox, you are going to lose because you are not doing what they have told. Okay, don't forget, those things are very important. In the previous part also they have mentioned, show the precipitates using arrows. So if you are not using arrows, instead of putting solid like this, you are going to lose marks. Those are the critical points that you should know. Okay, so they have mentioned here, see, use ox to denote oxalate. So don't use oxalate, C2O4, just use ox. Okay, so we are in the last part of the question. And they have given electrochemical cell, so you can see where this electrode chemistry is now. They have put this in the last part, but don't forget this is 2015. But when you come after 2019, according to the new syllabus, you know there are 3 physical chemistry question in part 3 along with 1 in the structured essay. So you need to understand the difference now. So the diagram given below shows a electrochemical cell connected in series. So this is one of the electrochemical cell, this is another electrochemical cell. They are connected in series. That is why here we have M22 plus, here we have M22 plus. There is no difference between the electrochemical potential of these 2 electrodes, but these 2 they have difference. Okay, and they have dipped in their relevant cations, and the concentration are 1 m. So typically it's like the standard condition, because it is 25 degrees Celsius, 1 m concentration. And the reduction potentials of the first cell, the standard electrode potential of the metals are given. So M1 it is minus 2.36, and M3 it is plus 0.34. Okay, and they have these questions. So this shows the direction of the electron flow. So here electron goes from here to here, and here it goes from here to here. Okay, giving reasons, identify the anode and cathode of each cell. Okay, so here this is cell 1. So think about the anode and cathode in cell 1. What do you think? How do you determine whether anode and cathode of cell 1? So we know in a cell, when you have this electrochemical cell formation, you know in the anode there is oxidation and there is electron flowing away from the anode to cathode, and the current flow from cathode to anode. So here when you think about this arrow, you can see from M1 the electron is flowing towards the outside direction. Okay, and also when you think about this potential of M1 with respect to M3, you can see M1 is minus 2.36. Here it is plus 0.34. So surely if the overall cell is considered, this is our cathode. Okay, when the overall cell is considered, this is our cathode because it has a more positive. And this should be our anode because it has a negative. Okay, so you can mention the electrode potential of M12 plus slash M solid is more negative than M32 plus slash M3 solid in the overall cell. Therefore, M1 electrode act as the anode and M3 electrode acts as the cathode in the cell 2, and here it is in the cell 1. So if M1 is anode in the cell 1, this M2 should be cathode in the cell 1, don't forget. Okay, and also in the cell 2, if M3 acts as the cathode, then M2 in the cell 2 should act as anode. So this is clearly indicated from the arrow as well. So you don't have to worry about much. You just need to write down the important points. What are the important points? You need to write down the potential of M1 is more negative than M3. Therefore, in the overall cell, M1 is anode in the cell 1, M3 is cathode in the cell 2. Then you have to mention about M2. So this is straightforward. Write the reactions taking place at the anode and cathode in each cell. So you can write cell 1. Okay, you can write cell 1, anode, and put oxidation. Okay, and underline this. Cell 1, anode, oxidation. Then write down the oxidation reaction. So what is the oxidation? M1 solid is oxidized to M1 2 plus 2 electron. Then the next one would be cell 1 cathode reduction, underline, then write down the reduction. What is reduction? M2 2 plus 2 electrons giving M2 solid. So similarly, you can write down the oxidation and reduction for the cell 2 as well. Okay, so don't forget they have asked in each cell. So you have to write down the cell 1 and cell 2 both. Then calculate the reading of the digital voltmeter. So automatically you need to understand. I will stop sharing here because I want to use the board now. Okay, so we have a cell like this. So we have two electrodes like this. So this is M2, this is M2, and this is overall connected to the other one. So here we have the voltmeter or the potentiometer. We have to find the voltage, and this was M1 and this is M3. So they are asking about what is the voltmeter. So normally, so here we have the reduction potential minus 2.76 something. We can check that. Yeah, minus 0.236, and this was 0.34, and they have given this color electron flow pathway, so we know all things. So this is cell 1 and this is cell 2. So now they are asking what is the potential shown here. Okay, so normally if you remember about your childhood, normally how do you connect? This is a series cell means. So you know this is a series cell. In physics also, when you have this cell connection in series like 1.5 volt, like 1.5 volt, the dry batteries, we say the overall is 3 volts. Why? Because in a series connection, we just add the voltage to increase the voltage. In a parallel connection like this, 1.5 volt, 1.5 volt. Don't forget, in a parallel connection, if you remember about your physics, we say the overall voltage is also 1.5. Because this is a parallel connection, same amount of voltage is felt. But the only difference here is the internal resistance that is going to change. Okay, if the battery has an internal resistance, it will change based on the current divided. Okay, but the potential is same, but here the potential is increasing. Now this solution is a series connection, which means the cell potential of cell 1 and cell potential of cell 2 should be added in order to get the overall potential. Okay, that is one point. Otherwise, if you want to get the overall, you know, so E cell is, you can write down E cathode cell 1 minus E anode cell 1. This is for cell 1. Okay, plus E cathode for cell 2 minus E anode for cell 2. Okay, so these are two equations. So if you want to take the overall cell, this P here, E cell, you need to add cell voltage of this one, cell voltage of this one. That is how in a series connection it works. Okay, so what is E cell cathode? E cell cathode means, E cell 1 cathode means this one. So it is this one. E M22 plus aqueous E M2 solid minus E anode. What is E anode? I will directly put the value now. Minus 2.36 volt. Plus, what is E cathode of cell 2? Plus 0.34 minus, what is E anode of cell 2? M2 2 plus aqueous, M2 solid. So what you can see from these two, this one and this one is going to cancel out because this is common in these two cells. Okay, so these two will be cancelled out. So finally you will have like since this is minus into minus plus, this will be 2.36 volt plus there is additional 0.34. So finally it will be 2.7 volt. Okay, so the reading here is 2.7 volt, right? So you don't have to write this entire thing. You can just write in the overall cell, E cell would be E cathode minus E anode, which is equal to 0.34 volt minus 2.36 volt, and you are going to get 2.7 volt. 3 lines, just 3 lines, it is done. This is just to explain you how it comes in a series connection. The electrode potential of one of the metals is going to be cancelled out like this. Okay, so this is the explanation for this part, and I will share the screen to explain the rest of the things. So we found the digital voltmeter, and the electromotive force of cell 1 is found to be 1.6. So calculate the standard electrode potential of M2. So what they have found here, I'll stop. So the electrode potential of this individual cell 1, they have found that separately in an experiment, and it is 1.6 volt, which means now they have found this one and they are telling find this M2 reduction potential. So it is straightforward because we know for this it is 1.6 is equal to E cathode, which is M2 plus. We don't know E cathode, we have to find that, minus what is E anode of cell 1? Minus 2.36 volt. So you can find E cathode is equal to minus 2.36 plus 1.6. So it will be minus 0.76 volt. Okay, so the potential of this is minus 0.76 volt. Okay, based on the information that they have given. Right, moving on. So this is done. So we have separately, they have found it somehow. It was 1.6, and we just need to plug into this equation in the board and find. Calculate the electromotive force of cell 2. So now this becomes again very straightforward. Now they are asking about this one. What is the electromotive overall? What is the overall value? So you know E cathode was 0.34 and minus E anode, which was here M2. We have found this as minus 0.76. So this should be 0. Plus 0.34 minus 0.76, and you know this should be added now, and you will get this one as 1.1 volts. So here it will be 1.1 volt, and here they have given it was 1.6 volt, and when you add these two, you can see we will get 2.7 automatically, which is the overall one that we calculated initially. So this cell would have 1.6 and this cell would have 1.1, and the overall you just need to add, that is what we get 2.7 here as well as here. Okay, so you can understand this is a nice question to elaborate the potential of individual cells like this, and overall what is happening. You can imagine what is happening when the overall is added, you will get the same values. Okay, and last. So we found this. SL2 is 1.1. If you provided only a metal of M4, so they are talking about a different story now, M4 and a solution of M4 plus. In addition to the above setup, suggest an experimental method in brief to determine the value of M2 plus M4. So this is uh, this is going to be very straightforward because this is the setup that they have already given, right? And also we know the potential of M3 2 plus and even with M1 2 plus. So what you have to just do is you have to make a cell like this. uh, in one of the sides you can have M4, which is our metal, and the solution should be M4 2 plus aqueous. Okay, and your other element can be either M1 or M3 because both of these potentials are we already know. So we can do here is we can, okay, now I will set up like M1. So my solution is M1 2 plus. Then I will connect this to a potentiometer and I will find its value. So I know this value. So if I know the value here, if I know this value and I know this value, this electrode potential of one of my electrode, so I can use the equation E cell is equal to E cathode minus E anode, and E cell is known from the voltmeter, and E cathode or either E anode I don't know, but one of the values we can suggest, like for an example I will take my E cathode as E M4 plus M42 plus M4 solid as my E cathode, and as E anode I can put my E M12 plus. So overall potential is known, my M1 potential is known, and you can find my unknown M4 potential. Okay, but don't forget this M4 can be either you can take as an anode or either cathode. If you take it as anode, it will give either positive or negative value based on its reduction potential. If we took it as a cathode, no worries, still it is going to give the same value because value does not change. If it is a positive, it will give a positive when you use it as a cathode. But if you use it as an anode, if the value is positive, it will give you as an anode. It's a negative value, so no problem in that. Okay, you just need to suggest, so simply draw this diagram first and tell that we can use either M1 or M3 as one of the electrodes, and the other electrode should be M42 plus M4 solid. Then we can connect this to a voltmeter to find the overall potential, and then you need to show this equation finally and tell using this equation we can find the reduction potential of M4. Okay, so that is done. So that's the way. So this is a nice informative question again. Okay, so 2015 we had many informative questions which are very nice because this covers more and more theory knowledge in your information. Normally we do this in the theory class, but it is also very good to have this in past papers. Okay,